Let's take a look at the 2014 E&M problem number 1. Scroll up a little bit to see the circuit here. Okay, so we have a power supply, an ammeter, and they just say that the current is measured by the ammeter, and then we have 3 resistors. 2 and 3 are in series with each other, which makes this branch have 100 ohms worth of resistance, and then those 2 guys are in parallel with R1, which they don't tell us. All right, they also tell us the potential difference, and they tell us the current. Note that the current is given to us in milliamps. We're going to have to account for that. And it says the current as a function of potential difference. So the first guy is the y-axis, and the second guy is the x-axis. And we're going to have to choose our scales. So let's see here, 2, 4, 6, 8, 10 volts, because we need to get up to 10. And then for these guys, we need to get up to, let's see here, 10, 20, 30, 40, 50, 100, 150, 200, yes, counting by tens. So 50, 100, 150, 200. That will make sure that we can get all of the data points on there. And as we plot these guys, we'll have go over to 2, to 4, over to 4, up to 55, over to 6, up to just under 100. 138 will be just under this guy. And then 155 will be that guy. All right, this looks like a little bit of a zigzag, and they did tell us draw a straight line. So I'm going to pause the video and get my ruler and draw a straight line. I have my line and my 2 data points on the line chosen. Notice that I have not chosen any of the data out of the data table. They want you to show that you understand that you're going to use the best fit line and not the raw data to get the slope. So we're going to be calculating the slope here, and let's take a look at what this slope is going to be telling us. So what we've done is graph Ohm's law in the form that the current is our y variable, our voltage is our x variable, and they told us this. They told us way back here the current is a function of the potential difference, and that means that the slope of the line is going to be 1 over the resistance. So slope, and they will want you to show that you understand that slope is change in y over change in x, and you choose 2 points that fall on the line. I've chosen the origin, and I've also chosen the point that has a y value of 130 and an x value of 8.4. So it would be 130 minus 0 over 8.4 minus 0. And you also have to keep in mind that the y-axis is in milliamps. So we're going to have to multiply by 10 to the minus third to account for the fact that the y-axis is in milliamps. If it were the x-axis in milliamps, then we'd be dividing by 10 to the minus third. So 1 over r equals slope equals, let's see here, what did I get here? Looks like 0.0155, and that means the resistance is going to be 64.5. So 64.5 ohms. Now, because this is a hand-drawn graph, they're going to have to give you some wiggle room in terms of what they accept for that slope there and then any future calculations that depend on it. If you happen to use the linear regression in your calculator, you should get 63.9 ohms. So 64 to 64.5 is not that far off. Now, simply scrolling down says, using the straight line, calculate the total resistance, and now we're going to have to calculate the value of R1. Before I erase all of my graph stuff on here, let's scroll back up one more time and take a look at this resistance situation here, where the total resistance that we just calculated of 64.5, so R total, is going to be a result of R1 and R2 plus R3 in parallel. So 1 over R total, which we know now, is going to be 1 over R1 plus 1 over R2 plus R3. So this will be 1 over, in my case, 64.5. Your graph will be slightly different. 1 over R1 plus 1 over 100. Now, this should provide a clue to you right here as to the limits of what R total can be. If you end up with a resistance greater than 100 here, you're going to end up with a negative resistance for your resistor there, and that's just awkward. So we need to do 1 divided by 64.5, or you can just use your slope again, minus 1 divided by 100. And then your last step, don't forget to take the reciprocal. And I'm getting 181 point fraction. So R1 equals 182, in my case, ohms. Yours is going to be a little bit different. The last time I did this by hand, I got 167 ohms. So there's going to be significant variation depending on what you get here. Because last time I got a slope, I got a total resistance of 62.5, and then this time as I was plotting it on my screen, I got 64.5. It's a little bit different every single time you do it by hand. I'm going to pause now and delete all these things that I need to get off the screen before moving on with the problem. All right, for parts D, E, and F, we're going to have 12 volts for a power supply. And now we want to calculate the current through R2. Now let's scroll back up and take a look here. If this is 12 volts, and then we have total current coming up, but then it immediately gets split and has to go between them, between the R2 and R3 and then R1. This means that what we have is 12 volts between those 2 points that I've marked on here, and R2 and R3 together get 12 volts. So taking a look at this again, current through R2 is going to be the voltage cross R2, resistance R2. Now, that current is going to be the same for R2 and R3. So I2 equals I3 equals I in that branch is going to be voltage across that branch divided by the resistance of that branch. Well, the voltage across that branch is going to be 12 volts because the one end of that branch is connected to the positive side, and the other end is connected to the negative side of the power supply. And then the resistance of that branch is going to be 100 ohms because we have 50 and 50. So 12 divided by 100, what we get for I2 is going to be 0.12 amps. All right, resistor 3 is now removed and replaced by what you see just below. So this is D, here's E1. Calculate the current immediately after the switch is closed. Okay, so immediately after the switch is closed, what we have here across the bottom here is just a wire. And we're going to repeat exactly what we did before, except the total resistance in that branch is 50 ohms. So I2, and I will call this prime to distinguish it from the previous one, is going to be still 12 volts, and it's going to be 50 ohms this time, which gets us 0.24 amps. Part 2, a long time after the switch is closed, what's going to be the current there? Well, after a long time, what we have is a filled up capacitor. When you have a filled up capacitor, it acts like an open switch. So let's draw an open switch there. With an open switch, there's no current going through that branch. So I2 final is going to be equal to 0. Because the capacitor is filled up, no current can go through that branch, and R2 is in the same branch, so no current is going to be going through R2. So your justification would be capacitor filled, allows no current, R2 in series with capacitor, has same current of 0. All right, part F. Suppose we get rid of that 4 nanofarad capacitor and we put 10 in its place. So let's scribble out the 4 and we'll put 10 nanofarads. Well, if you come back up here, do you see any capacitor in this Ohm's law calculation? You have voltage, you have resistance, and that will get you current. Capacitance has nothing to do with this. So it will be equal to. So size of capacitor irrelevant to initial current.